Welcome you all. Welcome you all to the second session of the third day of this FDP. I am Professor Dept Bhattacharjee, Chairman of this session. And now, in this session, the second session, the lecture will be delivered by Dr. Hussain, and the title of his lecture is Role of Clay Minerals in Designing Organo-clay Hybrid Materials for Sensing Applications. To give a brief description about Dr. Hussain, I must say that his major fields of research interest are organo-clay hybrid films, freight, biosensors, biomimetic surfaces, Langmuir film, molecular aggregates, organic switching, and memory devices. He is working in the Thin Film and Nanoscience Research Laboratory of the Department of Physics, Tripura University. He worked as a postdoctoral fellow in the Catholic University of Leuven, Belgium, and also he worked as visiting scientist to the Japan, Yamaguchi University to Japan. And to his credit, he already published 130 high research papers in high impact factor international journals, and already 9 scholars have been awarded PhD degree working under his supervision. And he also run several projects from DST, CSIR, DBT, and others. I am now requesting Dr. Hussain to deliver his lecture. Thank you all.
Good morning. Thank you, sir, for your kind introduction. It's my pleasure to be introduced from my guide. I want to share with you all that Professor Dept Bhattacharjee was my PhD guide and also my teacher. So thank you, sir. Today, I am going to talk on effect of clay mineral in designing organo-clay hybrid materials for various interesting properties, including sensing. Clay is one of the oldest material in this earth, we know, and obviously it comes under the purview of material science. Material science deals with the understanding of the history of processing of the material, that is how the materials is being prepared, and then the way of processing, how it influences its structure. And based on the processing as well as structure, it can have some kind of property. And then based on property as well as performance, the material should have some kind of applications. So one can say that if someone study the preparation, then structure, then property, performance, as well as applications, this all things comes under the material science. Properties may be mechanical property, electrical property, magnetic property, or optical property, and so on. There are numerous applications. Without material science, you cannot imagine the modern day life. And main applications involve electronics, communications, medicine, transportations, manufacturing, everywhere. Whatever gadget you are using, there are some kind of materials as well as material science. And material science, you know, the oldest science in this world, journey of the material science and human to this earth are almost parallel and started together. Human civilizations are often divided into ages according to the materials that dominate in the society. In our lower or school days, we have studied, for example, Stone Age, Bronze Age, Iron Age, Steel Age, etc. And the decade was named based on the materials used during that time, mainly. Now we have entered the modern material age, the age, plastic age, maybe in the last half of the 20th century. And at present, we can say that we are in the age of silicon age. And this kind of new materials have, we can say that, transformed our lifestyle forever and made this vast world or universe maybe as a global village. Just for information, let's have a look the status of material science in India. If we compare number of publications with world, India ranked 6th. And then research share in all areas with respect to output, if we compare to the rest of the world, we contribute 3.88%. But in case of material science, India's share with respect to the world is 6.42%. That means in India, we are more emphasizing on material science compared to the other field. Average impact factor of papers in all subjects published by Indian scientists is less than 1. But in material science, average impact factor is almost 2. And almost all institutes, we have some kind of material science research going on. Now, what kind of materials we are interested in near future? We believe that we should have some kind of design material which will be built using molecular building blocks at the molecular scale in a predetermined or desired manner to have certain predetermined property, so that based on this property, we can apply the material according to our requirement. And in that regard, we can say that in nature, we have several material. In periodic element, we have several bioorganic molecule, amino acids, nucleic acid, lipids, etc. Then we have numerous man-made organic molecules. They are derivatives. These materials or these elements will act as synthetic building blocks, very similarly like that of English alphabet. Using the alphabet, we can design any words, then sentence. Similarly, using this kind of fundamental material or elements, we can join together, we can make complex in a determined or predetermined manner. So this is the main requirement for the material scientist in near future. Now, let's come to today's topic. We all know about soil. Soil is alive with living organism. Without soil, we cannot imagine the lives in this world. It supports life with its naturally occurring nutrients, minerals, making it a perfect planting medium. It is a complete and self-sustaining ecosystem. Without soil, it is hardly imaginable life in this world. We know sand, silt, clay, and different organic material make up soil. In lower classes, we have studied there are different kinds of soils, loamy soil, clay soil, sandy soil, etc. These are mainly based on the composition of the soil as well as some physical property, for example, porosity, etc. Therefore, we can say that clay is a subset of the soil family. Clay exhibits plasticity when mixed with water and becomes firm and hard on drying. Due to these properties, clay are used in many applications. Main applications include construction, industries, crockery, pottery, then medicinal application, then cosmetics. But here, I am interested the use of clay in designing organo-clay hybrid materials. Why? So that we can manipulate the properties of the organic material when we incorporate it on the clay systems. And this kind of hybrid systems are very much interesting with respect to optoelectronic applications, including sensing. And throughout the world, several research groups are emphasizing work on these organo-clay hybrid systems. Now, what is clay minerals? Clay minerals represent an important group of layered inorganic materials. They swell in aqueous dispersion into single sheet with thickness 1 nanometer, diameter may be of the order of 1 to 2 micrometer. They are natural nanomaterial having colloidal size, high cation exchange capacities, large surface areas, surface reactivities, adsorptive properties, high viscosity, and transparency. Another interesting property of clay is intercalation. That is simultaneous incorporation of polar as well as ionic or neutral material into the interlamellar spaces of clay layer, and this provides the clay material as one of the important host material to prepare organic inorganic hybrid material. Clay minerals mainly are composed of negatively charged aluminosilicate layers. In between the layer, we have positively charged interlayer region. And this each layer is composed of fused sheet of tetrahedra of silicon oxide, then octahedra of aluminum or magnesium or these ferric oxides. And the arrangements are like that. 1:1 means one silica layer, then one alumina layer, in between other charged material. TOT 2:1 means silicon layer, then octahedra layer, then again tetrahedra layer. This kind of structure. These are very general. Therefore, we can say that basic building blocks of clay minerals are silica tetrahedrons and alumina octahedrons. Silica tetrahedrons, this structure is just showing here. This repeat unit of silica tetrahedron forms silica layer or silica tetrahedra sheet. Similarly here, alumina octahedrons, this one, and the repetition of this unit forms this alumina sheet. And then ions, molecules, sheet. Sheet means this silicon sheet or alumina sheet. Then sheet upon sheet, we say it layer. Then layer upon layer, we say it crystal. Layering of silica and alumina sheets together result in different types of clay. And also based on the composition of the interlayer space, mainly different types of clay are nomenclatured or differentiated based on the layering of these sheets as well as composition of the interlayer material. And the ratios are like that: 1:1, that is TO, then 2:1, that is TOT. Here again schematically shown, this is silicon tetrahedral layer sheet, alumina sheet, then again silica sheet. So this is a TOT layer. Here again is shown in a block diagram. This is just for understanding. The major clay mineral groups are kaolinite group. These are 1:1 TO type clay. Here schematically shown, this is layer, in between other charged material is there. Then mica, this is TOT type clay. Examples are montmorillonite, maybe saponite, leponite, hectorite, and in our lab we work with this kind of TOT type smectite material, mainly hectorite, leponite, saponite, etc. Then chloride group, these are 2:2 TOT with O interlayered, and these are rich with iron and magnesium. Now, I mentioned already, swelling is one of the important properties of the clay. So schematically, I have just shown here for easy understanding. This is a crystal having this layer in between charged material. So when we put them in aqueous medium, then what happened? Swelling, then this layer got separated from the crystal and structure become like this. This is then we can say that these are swollen. Here again is shown, it's a sheet, either maybe silica or aluminum. So by swelling, we can separate or make the clay crystal into single sheet following proper procedure. Again, the mechanism of swelling, there are two mechanisms proposed. One is due to hydration of exchangeable cations. These cations in between the layer, when they get hydrated, when water molecule enter in between them, then this layer got separated. Another is osmotic swelling. This is difference in the ion concentration and principally in the cation concentration at the surface of the clay layer and in the pore water. Due to this difference, that is concentration here and then here. Here concentration is more, so water molecule go inside the layer and the layer got separated. So due to this osmotic action, the clay layer got separated, that is swelling occurs. And this swelling is helps us to have a single clay sheet from clay crystal, and the size of the single sheet is of the order of less than 1 nanometer. So it's a natural nanomaterial. Another property of clay is intercalation. Intercalation means it's possible to incorporate the foreign material, that is maybe organic dye or polymer or maybe biomaterial of your interest in between the clay layer or onto the clay surface. So this is called intercalation. Here just schematically for easy understanding shown, this is a clay crystal. This is the foreign material we want to incorporate. Here it is shown some material in between the clay layer, some on the surface, and through sonications or as well as putting a magnetic stirrer, it's possible to exfoliate, that is to have single clay sheets with your foreign material attached onto the surface of the sheet. Here also it is shown again. This is the clay. This is the organic molecule. It's possible to intercalate in between the layer, or maybe you see the outside of the clay crystal. This is called intercalation, and this is a phase separated structure, that is clay and this organic material is separated. Here also polymer, you can have this kind of clay polymer structure, polymer outside the crystal layer or in between the clay layer or surrounding the single clay sheets following proper procedure. So it's possible. Another important property of clay is cation exchange capacity. Cation exchange capacity is the total capacity of a soil or clay to hold exchangeable cations. And this is mainly depends on the strength of the cation. Adsorption depends mainly on the this lyotropic series. That is, this is a series based on the reactivity of the ions with the interacting capability with the solvent material. So, and also based on the charge density as well as balance and size. So due to this kind of preference, materials can, cations can exchange with the clay material. Normally, clay surface has negative charge, and this negative charge attached with some kind of cation as shown in this cartoon. This is Ca+2, Mg+2, Na+2. Now, following proper procedure or creating proper environment, one can exchange this Ca+2 with other cations, or Mg+2 with other cations, or Na+2 with other cations. This is called cation exchange capacity, and this is measured in terms of the total exchangeable cation present in the clay surface, and the conventionally expressed in terms of mega equivalent per gram. Here again, it's shown. This is a clay crystal of 3 layers. Each layer is a TOT type clay, and in between you can see the dye molecules are intercalated. Some are attached in the surface and some are in between the clay crystals. Here again in between the sheets. So this is shown just to have an idea that one can play with the clay and the other material, and can have a complex system or hybrid system in a desired manner, but of course with proper environment and following proper procedure. We are interested to explore new organo-clay hybrid nanomaterials with different functionalities, such as sensing, biosensing, catalysis, optics, electronics, etc. And for this, we are studying the organization of clay particles and adsorbed molecules. And also, we are interested to study the fundamental property of single clay sheets, for example, mechanical property, etc. And then we do some studies on the effect of clay minerals on the fluorescence resonance energy transfer between the organic dyes. And also we try or give some effort to have idea about this film hybrid film formation process. So as a whole, we are interested to prepare or design some kind of supramolecular assembly so that we can have some interesting property having some applications. These are some related publications. These are optical sensor based on clay organic hybrid systems. You can see this mercury sensor, then cholesterol, arsenic, hard water sensor, pH sensor, ion sensor, DNA sensor, etc. We have designed based on the clay organic hybrid material. And in all these works, clay has certain rule. I will give one or two examples. Here we have prepared some kind of aggregate of organo-clay hybrid systems. These kind of systems are very suitable for sensing, biosensing, catalysis, optics, and electronics applications. And these are related publications. Other than clay, we are also working on designing organic memory devices. And for this, we are studying the switching behavior of organic material assembled on thin films, and mainly to demonstrate their applications in ROM, RAM kind of things. You know, normally at present, mainly silicons are mainly used, but here throughout the world, a lot of work are going on to design memory circuits using organic material, and we are also doing this kind of works. This is because, you know, silicons are very limited and abundance is also limited, but organic material, you have vast variety, you have flexibility, you can change the functionality by manipulating the structure. So it's interesting to try memory applications using organic material. Now, why we are interested in organo-clay systems? This is because the planarity of the pi conjugated system of the confined organic molecule is increased, that is, which extend the pi conjugation length when we incorporate the organic material in between the clay layer. Also, the fluorescence quantum yield of the dyes is enhanced due to the suppression of vibrational motion of the confined molecules. And this again contribute to the interesting optoelectronic behavior. The clay mineral can accommodate a high density of organic molecules in its interlayer space or on the surface of the clay layer without aggregation. So one can control the aggregation behavior by just incorporating the dye molecule in between the clay or clay surface. Again, due to, I have already mentioned the swelling behavior of clay, one can swell the clay by putting them into the aqueous environment. Again, by drying, one can decrease the, one can have the previous structure, that is, one can control the layer thickness or gap between the layer by simultaneous wetting, that is swelling and then drying. And in this way, one can control the organization of the incorporated molecule. This is very interesting. I will give one or two examples. Also, the organization of the organic molecule can be manipulated with ease to control the properties. You know, the organization of the molecule is very important with respect to electronic and optoelectronic behavior. Therefore, organic molecules confined in clay organic hybrid system often exhibit unique electronic properties that are not observed in their solution or crystalline states. In this cartoon, I am showing, you can see if you prepare the film or if you assemble your material on this substrate. Now, in case of organo-clay hybrid system, what happens? There are two kind of organizations. One is organization of this dye onto the clay surface, and then the organization of this clay in the substrate, and at the same time organization of few or dye will organize on the or fix on the substrate itself. So dye molecule organize on the clay surface or in between the clay layer, and few dyes in on the substrate surface. So if you can control the organization of these two kinds, then you can control or you can have some interesting property. In other way, by controlling or by manipulating the organization of the dye molecule into the organo-clay hybrid systems, you can manipulate their behavior. So that's why it's very interesting. In this cartoon, it is shown that you can see these are dipolar molecule. So in between the clay layer, the molecule are organized in such a way that net resultant moment is not zero in this one first case. But here you can see the net resultant moment is zero. Accordingly, property is also affected. Here you can see these are inclined, but net resultant moment is not zero, but it is with respect to first case, it's different. Similarly, here you can see, and these are, you know, unorganized systems. Again, in some cases, you can have the total net resultant moment zero, some may be not equal to zero. And in this way, by controlling the structure, you can control the property as a whole of the system. So this is interesting. Now, how we are preparing the organo-clay hybrid systems. For this, we follow several techniques. One is Langmuir-Blodgett technique, then self-sending films, then spin coating technique, layer by layer self-assembled technique. So we follow this kind of techniques to prepare organo-clay hybrid systems into thin films. These are some LB systems to prepare LB films. Yesterday, one speaker, Shumobruto Da, he explained LB systems in a very lucid way. So I am not going in details in that. This is a simple system. This is a system attached with inverted fluorescence imaging facility. So you can have idea about your material when you are preparing the films. Here you see the system is attached with Brewster angle microscopy system. So here also you can have the idea, you can have the images, BAM images of your floating material. In these systems, LV system, there are two steps. One first step is you have to prepare your material onto the liquid interface, maybe water, mercury, or whatever may be suitable liquid you will put in the trough. Then you spread your material, then you prepare a floating layer. Then you transfer the material onto solid substrate. So these two instruments help you to image your material on the trough. Here, just a small animation, how this can be done. You can see this trough first. We spread the material, then we compress. Then we form a two-dimensional molecular layer. Then we transfer this layer onto the solid surface or substrate for further study or application, whatever may be. This is a very simple technique, but you need much attention. Just for understanding, I have shown some kind of, you see the water plant, floating water plant. All of us know this kind of things in the pond, and sometimes we compress them with bamboo. Same thing happened in case of our LV systems. We put the molecule, then we compress with a barrier. And in case of this plant, what happens, certain time will come, then all plants touch each other. They form a compact layer. And if we further compress, then what happens, some plant will slide upon each other or maybe go down to the bamboo. That is, we can say it's collapsed. Same thing happened here also. And once your film is prepared, then we deposit as shown in this animations. This is for this understanding, I have shown another picture here. You see heated milk, cream. We all have seen this cream upon the heated milk. If you dip a spoon and take out, then what will happen? This cream layer will stick on the spoon. Same technique here. But of course, in real experiments, this is molecular level phenomena. You cannot see it, you cannot hold it. A minute change in environment, maybe with respect to vibration, maybe with respect to contamination, it will change, it will affect the property or your whole system. So you have to be very careful. A lot of factors are there. For example, properties of the material. If it is charged, then maybe electrostatic interaction with the material and the substrate. There may be van der Waals interaction. There may be dipole-dipole interaction. So many issues are there. So you have to be very careful for your real experiments. So just this is an idea, but we are interested to prepare organo-clay hybrid systems. For this, what we do, I already told you that it's possible to exfoliate by swelling clay into single clay nano sheets. So for this, what we do, we prepare clay dispersion using water, and then we put in magnetic stirrer for more than 24 hours. Then before use, we put in ultrasonication for several minutes. Then we put this dispersion in the LV trough instead of pure water. Then we spread some selected molecule on the surface. Then what happened when this clay, they are negatively charged, and normally we choose this molecule as cations, but it depends. You have to play, you have to optimize your system. When this clay comes close contact with your dye, then through electrostatic interaction as well as cation exchange reactions, they got attached. Here you can see in the second picture, attached with this dye molecule. Then we compress with the barrier. Then we form a compact layer. Then we deposit on the substrate. So this is your organo-clay hybrid system. Here again, and when you spread these organic materials on the surface of the clay dispersion, then clay materials comes onto the surface, and this is a time-dependent process, and one can monitor this. There are several ways of doing this. For example, one can look the change of the structure of the floating layer with time using BAM, using FIM also. But here I am showing one experiment. This is called IRRAS, infrared. Any problem? Okay. Infrared reflection absorption spectroscopy setup. You know, clay, we have SiO4. So there is they vibrate. So through IR study, we can measure this vibration. So here is an arrangement. This is infrared reflection absorption spectroscopy, where the light is allowed to fall on the floating layer, and the reflected light is being recorded with monochromator. And if we plot the intensity of the vibration of the SiO bond, then you can see here initially intensity was very less, and with time the intensity increases, and after some times it flattens. That means your almost all dyes are attached with your clay. Similarly, here I am showing two images. One is this film is deposited just after 5 minutes of spreading the dye molecule on the clay surface, and this one after 30 minutes, and you can see more number of clay in this image. That means it's a time dependent process, and you can have idea using this kind of experiments. Second process is self-standing organo-clay films. Here what we do, we prepare the clay dispersion as mentioned earlier, then we put the dyes, suitable dye in the dispersion, we put in magnetic stirrer, then ultrasonication, then we have a filtration system. Here we use membrane with pore size fraction of micrometer, and then we put the mixture here, and we use a vacuum pump to suck here the air from this so that the filtration water can come here, and in this way the material layer formed on the membrane. And once the film is formed, then we take out the membrane and we can peel off the film from the membrane onto any substrate we want, and this is a self-standing film. Then we use spin coating films, and this is very common. A substrate is there. Again, we prepare the clay and organic material mixture with desirable concentration. Then we put the drop on the substrate and we spin this. And there is an arrangement with vacuum system and then motor. And we can control the speed. We can control, give some certain time for spinning. Then material spread due to this centrifugal force. Then repeating this thing, we can prepare a desired thick film according to our requirement. So this is a very simple process. Then this is another process, layer by layer LBL film deposition system. It's based on the interactions of the oppositely charged material. It's a self-assembly system. What we do, we select negatively charged slides, and then we put it onto the material, selected material, maybe organic with positive charge or cationic. Then we dip into the solution. Then through electrostatic interaction, the molecule attached with the slide, we take out, we wash it, we dry it. Then the layer is like this. This is with organic material layer. Then we deposit it into clay dispersion, and due to cation exchange reaction as well as electrostatic interactions, clay are negatively surface. Then this layer is positive, so they again attached at the surface, and this is a bilayer of organic material and clay. And by repeating this whole process, we can have we can prepare the film with desired thickness. These are some representative images of the organo-clay systems prepared using LV technique. You can see different size and texture, but thickness is less than 2 nanometer. This is saponite, then leponite is plate-like, then Wyoming, then hectorite, it is like particle. So, so this is just some representations. Okay, so let's see some example. This here, it's the pyridinium derivatives, and clay is saponite, synthetic saponite. What actually done? This is a self-stand. We prepare a self-standing film using saponite and clay with different concentration. This is, you see, the incorporated dye concentration is 0.05% of the CEC, then 1% of CEC. 1% of CEC means if we have 100 number of exchangeable cation, then we are exchanging one cation with dye. 10% means 10. So similarly, we prepare films, and interestingly, we have seen in the first column, you can see the color. This is naked eye and taken using a simple camera, maybe mobile camera. you can see the images. This is blue, and in the for all first column for all concentration, this is SPPR without any treating, without any then after that what we do, what we did, we put some solvent in the film, and maybe a drop of water, or maybe DMSO, or maybe chloroform. Then again we observe, and in under normal light and with naked eye, we didn't see any change. This is shown in second column. You can see second column. But interesting thing is that after putting the solvent, when we expose the film under UV light, we see the colors. In the last column, you can see the colors. And from this experiment, we selected this 10% CEC. And if you concentrate in this line, you can see first one is SPPR, second one is putting your solvent, DMSO, water, whatever, maybe we have checked, this is a solvent independent phenomena. All solvent worked. But DMSO is used because DMSO is high boiling point. So in normal room temperature, it's easy to work with. But third one, you can see it's almost yellow. And this is under UV. But with normal light, it's unchanged. So we tried to understand why this happened. This is, I'm not explaining all these kind of things. This is some spectroscopy. We did some spectroscopy to have idea why this happened. So we have seen the spectral feature of this, the SPPR film and the swollen film, that is after putting the solvent, is quite different. And in fluorescence, the swollen film showed longer wavelength, broad structureless band. And this is mainly due to excimer. Excimer means some kind of aggregation. One excited state molecule and one ground state molecule overlap each other, and they form some kind of aggregate. Accordingly, their spectroscopic behavior changes. So to have more idea what we did, we do lifetime measurement also. And we have seen that this longer wavelength band, broad structureless band, due to this swollen film, has almost 18 times longer lifetime than the SPPR film fluorescence spectra band. And excimer band, mainly excimer has mainly longer lifetime. Again, we studied the XRD, and from XRD, what is seen is that for the SPPR film, the gallery height was 0.48 nanometer, but in swollen film, it was 0.93 nanometer. So this is almost double than the normal film. So from this, we conclude that in case of swollen film, two pyridinium molecule come stack together and form excimer through pi-pi stacking. Accordingly, it shows this longer wavelength band in fluorescence spectra. But excimer is an excited state phenomena. That's why no change in absorption. That's why no change in normal light. Only when it's excited with UV light, then fluorescence changes. That's why under UV only we can see the color change. And interesting thing is that SPPR film, when swollen under UV, it shows yellow color. But if we wash it with water, then DMSO come out from the film, and again it shows the original color. And this is a reversible process. Maybe 50-30 times it's possible to change this color of the same film. In this cartoon is shown, here you see one molecule in between the layer. In swollen state, excimer, two molecules stack together. Accordingly, this longer wavelength band formed. And it is proposed that these findings can be used to design some kind of secret writing. Here, in the first film, this is SPPR, and then what is done with a hearing bird dipped in DMSO, it is written, say, TU on the film. And the lower one, it's already written, but under normal light, visible light, you see nothing is seen. But when this is exposed under UV light, you can see TU is clearly seen. So it can be said that it can be used for secret writing. Again, after washing, one can wash out, and under UV also you can see no color change. So it's an important organo-clay hybrid system, may be used for secret writing, for optical memory applications, etc. This is another example where we have shown one indolil derivative and clay we prepared the film. You can see the prepared film is colorless, but when we heat it, it becomes red. Then when we swellen it, it becomes yellow. And this is mainly, and here it is shown for different concentrations. And this is mainly because when we heat, then oxidation occurs, again color comes, and molecule become flattened, and pi conjugation become extended, accordingly red color appeared. But when it is swollen, then some kind of twisting occurred in the molecule, according to conjugation disturbed, then color changes to yellow. And this is again reversible, and this is possible using simultaneous drying and swelling. And here the schematic, we have shown the mechanism. Here you can see molecule flat in the dried condition. This is normally prepared condition. The layer height is 0.636 nanometer. This is again heated, and gallery height decreases. That means maximum flattening occurred. Red color appeared. Here are swelling. Again, the gallery height increases, and this is done through XRD measurement, and twisting occurred. Accordingly, yellow color appeared. Here we are showing another example of organo-clay system. This is a polydiacetylene material. Actually, diacetylene, I have shown here schematically diacetylene monomer, and when we expose this material under UV through polymerizations, actually it's a photochemical polymerization. It forms polymer PDA, and PDA has two phase. One is unstable blue phase, then again red phase, and it's possible to convert from blue to red under different stimulus. For example, light, maybe temperature, maybe pH, maybe presence of any foreign particles there, and this property gives the scope to use this material as an important sensing material. Because if you prepare a film or material in blue phase, then you expose this under your material you want to sense, and if it is changed its color to red, then you can say that yes, it is a sensor. It can give idea about the presence. And for spectroscopy, you can see the blue phase. This absorption band is here near about 650. Red phase here, and fluorescence. Blue phase, no fluorescence, almost no. Red phase, strong fluorescence. Here we prepared one film using clay, is a saponite, then an imidazole derivative, an organic material, and then PDA. And what we have seen, you see, first picture, it's we prepared the film, then using UV, we converted the film into blue phase. And this is the image using a normal optical camera. Then we expose this film under alcohol. You see, film after 5 times puff, after 1 hour of consumption of 2 peg alcohol. You can see the picture B is red. That means this polymer changes into red form. Accordingly, color appeared, and this is again after some time, again exposure, maybe how many times? 4 hour of consumption of alcohol. Still, you see the color change. So just by with naked eye, just observing the color change, you can have idea about whether a person is drunk or not. Here you can see the corresponding fluorescence microscopy image. This is in blue phase. This is before exposure, the first one, and second one is after exposure, and you can see the clear polymer structure is shown, visible. At present, available alcohol sensor is based on conductivity or resistivity change, where a coating is there on a material, and it's actually conductivity changes when exposed onto alcohol. And of course, for these instruments, one need a battery, then it's connected with your film, then you need an ammeter for measurement of current, then of course you have to optimize or calibrate. So it's a bit expensive, but in our case, just it's a piece of paper, just like litmus paper. You just hold it in front of a drunk person, and you can see just color change, and you can have idea whether the person is drunk or not. And regarding quantifications, what you have to do, you have to select some pixels into the image, then you take the RGB combination of the color, then you prepare some algorithm, and based on the this intensity of the RGB with concentration, you can develop some algorithm, and you can have idea about the concentration also, so you can quantify also. Okay. What about your time? Okay. So and in next few example, I am showing the effect of clay on fluorescence resonance energy transfer. And these are some publications related to this. Actually, fluorescence resonance energy transfer is an non-radiative electrodynamic phenomena where one molecule is excited using some external source. Molecule absorb photon and go to the excited state. Then, in a non-radiative way, this molecule gives energy to a neighboring molecule, and this molecule excited to the excited states and radiate a photon. So in here, two molecules normally, say one molecule is a donor, it's normally accept the photon or energy from the source, then it's excited and it gives its energy or photon to the neighboring molecule, and we say it as acceptor, and acceptor show fluoresce. So it's a two-step process, and it's very interesting because this energy transfer process depends several parameters. For example, distance between the two molecules, and typically the distance between donor acceptor should be of the order of 1 to 10 nanometer. There are other factors also. For example, overlap of fluorescence of the donor should be overlap with the absorption of the acceptor. The orientation also have some kind of rule, but the main issue is distance. The distance is 1 to 10 nanometer, and it's of the order of molecular level interaction range. So you can have idea about molecular level interactions by studying the energy transfer between molecules. So this is interesting. And if you can manipulate, or if the distance between the two molecules, that is donor and acceptor, changes, or the relative orientation of the molecule changes, or the spectral overlap, etc., changes by somehow, then your energy transfer efficiency or extent of energy transfer changes. Therefore, it can be said that if presence of any external agent affects these factors, then what will happen? Efficiency or extent of energy transfer will change. In other way, we can say that by observing the change in energy transfer efficiency, we can have idea about the disturbance or about the presence of other factors. Therefore, it is possible to sense the presence of external agent by observing the change in energy transfer efficiency. Here, we have selected two molecules based on the theoretical criteria, so that energy transfer occur. Theoretical criteria means absorption of one molecule should overlap with the fluorescence of the donor. So it is there. Then both molecules should be highly fluorescent, that is high quantum yield. We have also, based on this, we have selected these two and studied the energy transfer. And we have seen that in absence of clay, the energy transfer efficiency was 64.2%. But in presence of clay, it becomes 97.7%. Almost all energy absorbed by the donor, that is our NK, transfer to the acceptor molecule in presence of clay. And this is mainly because you can see in this table, we have calculated the orientation factor, the distance between these two molecules as well as efficiency. And from this, you can see that the distance between the two molecules in clay becomes less compared to that in absence of clay. And since it's a distance-dependent phenomena, once distance is lower, the efficiency enhances. Again, you can see that the overlap also increases in presence of clay. So these two change in presence of clay actually affects the energy transfer and increases this efficiency. Again, here another example with acrylflavin molecule, then rhodamine molecule. This is donor, this is acceptor. Here, aqueous solution, we have seen that energy transfer efficiency was 11.37%, but when we put clay in clay dispersion, efficiency becomes 78%, almost 7 times. And this is again because distance, you can see lower from 8 to 5.33 nanometer. Schematically here, I have shown that you see first case, this is in homogeneous solution, is molecules are randomly moving, distance is higher, so efficiency is also less. But when the molecules are adsorbed on the clay surface, they are attached with the clay system and the distance become lower. Accordingly, efficiency, you can see, become 78.17%. We have used this result to devise several sensors. For example, say hard water sensor. Hard water actually based on the concentration of certain ions, for example, magnesium and calcium, if process certain limit, we can say it moderately hard or very hard water. So what we did, we studied the effect of presence of this kind of ions in the solution on the energy transfer between these systems. And we have seen that in uniform solution, in absence of these ions, you can see the energy transfer is 11.37%. When we put either calcium or magnesium or both, in all three cases, efficiency decreases. But you can see that the decrease is from 11 to 1.7 or 11 to 5.2, 11 to 4.38, decrease is very less. So it's difficult to differentiate. Then what we did, we put clay in the system. Then what happened, you can see instead of 11, in case of energy transfer between only dye, in presence of clay, it reaches 78%. Then we put this magnesium, calcium or both. Then you can see that the energy transfer decreases from 78 to 37% or 78 to 51% or 48%, and the difference is very good so that you can distinguish. And this is because in this schematic you can see that normally in solution the molecules having large distance, so efficiency is very less. But in presence of clay, molecules are attached in the clay layer, so distance is very less, efficiency is very high. But in order to check the effect of these ions, what we did, first we put the ions in the clay system. Then what happened? The ions are attached because Mg+2, Ca+2, these are positively charged, clay surface is negatively charged. They are attached in the clay systems. And then we expose this system on the water to be studied. Then, in the dye. Then the dye are attached. But already some negative charge on the clay surface is being attached, neutralized or attached with the calcium or magnesium ion. So here dyes are attached relatively higher distances. Accordingly, energy transfer efficiency is also less. But here, rule of clay is that clay helps us to differentiate, or in other sense, we can say that sensitivity of the sensor enhances due to the presence of clay. Here, just shown the change in efficiency with different concentrations. So based on this result, we put this graph where we just by observing the efficiency, we can say that if the efficiency lies, say greater than 48.2%, we can say that this is a soft water. If the efficiency lies say less than 48.2 and greater than 13.5, we can say that this is moderately hard water. If it is less than 13.5, then we can say that this is a very hard water. And also in the same way, we have designed other sensor, say arsenic sensor, then ion sensor, DNA sensor, cholesterol sensor, pH sensor, etc. DNA sensors, we have designed several sensors. It's possible to study using this about different condition of DNA. For example, we know DNA denaturation occur. It can remain a single strand, coil form, double strand. So our sensor can give you idea about this conformation in changed environment. So if you are interested, you can read these things. I am not showing all these results here. Another example, effect of clay on second harmonic generation. Second harmonic generation is a non-linear optical effect, and in this case, two photons having same energy interact with non-linear medium, and results a photon having energy double than the incident one, or wavelength half. This is a non-linear phenomena, and for this, the fundamental requirement is that your system should be non-linear material. That means it should not have symmetry, or it should have non-centrosymmetric structure. Using LB film, we demonstrated that even molecules which are symmetric in structure, we can have a non-centrosymmetric layer of J aggregates of that molecule, so that the layer, all those molecules itself is not SHG active. It's not showing second harmonic generation, but the layer show second harmonic generation, because as a whole, the layer is non-centrosymmetric. Schematically here shown, you can see this is a stacking of molecules of one layer. And you see, if you join a line here, in the first one, above one, you can see it's a layer of two molecules, but it's a single layer. If you draw an imaginary line, it's not symmetric. But if you have two layers, and if you draw a line along the center, you can see the whole system is symmetric. So if you prepare a J aggregate of a single layer, maybe stacking of more than one molecule, but it should be a single layer. This is important. Then it is a non-centrosymmetric structure, and it is SHG active. So we demonstrated this one. This is just J aggregate characteristics, so I am not explaining this. This one also. Okay. So here I am showing the SHG signal, second harmonic generation. This is, you see, in absence of clay, first one. So the black line shows the SHG signal for recently prepared films. But after 7 days, we have seen, you can see red one, the intensity decreases. This is because LB films of organic molecules are mechanically in certain time unstable. So intensity decreases. But when we incorporate clay in the system, you can see that even after 7 days, or we studied more than that also, you can see the change in the intensity is less with respect to the freshly prepared one. That means presence of your clay enhances the mechanical stability. And this kind of second harmonic phenomena is important for application like as second harmonic SHG microscopy, or maybe laser application. You can there are several examples also. You can have say green laser using longer wavelength using this SHG effect. Green laser, say 523 nanometer from a source of say 1064 nanometer, passing through a nonlinear medium, maybe KDP crystal, etc. And then you can have this green laser also. But these are some examples. Other examples are there also internet. This is again example. You can see that in this graph, without clay, SHG intensity is lower, but in presence of clay, SHG intensity increases. Therefore, we can say that clay materials are very interesting or promising for preparing organo-clay hybrid or supramolecular structure having some interesting properties, and by controlling the organization of the organic molecule in such organonuclear system, we can manipulate the properties such as colorimetric switching or energy transfer or J aggregation or SHG, etc. for suitable applications. Therefore, as a whole, we can say that organonuclear hybrid films are very promising for future technological applications. So with this, I conclude my lecture. So if you have any query, you can raise or you can ask.
Okay, thank you, Arshad, for your very interesting lecture, and also your recent development of your work in the lab. And I am now there are a large number of in the chat. I am seeing some questions. First thing is that in place of DMSO, any other solvent of high boiling point can be used.
Yes.
And also another question, instead of DMSO, if we use deionized water, what will happen to the film? Whether DMSO has such high boiling point?
Actually, it's nice. Actually, it's due to swelling. When we incorporate the molecule in between the clay layer, in dry condition, the distance between the layer is less. Only one molecule can lie flat. When we swell by wetting the film, then distance increases through swelling, and then two molecules stack together to form excimer. It's due to mainly swelling. Now the question, how we will swell the film? It's possible to swell using any solvent. We have checked it. It's a solvent independent phenomena, but we prefer DMSO because DMSO is having high boiling point. So at room temperature, if you use DMSO, you can put your system for some long time. If you use water or maybe chloroform also, methanol also possible. But if you put methanol or water, methanol is very high volatile. So automatically it will dry out. So it will convert from excimer to monomer. That is, it will dry out. Similarly, water also, after some time, water will dry. That's why we prefer solvent having high boiling point. Otherwise, any solvent is okay, no problem. Deionized water is also okay, very good.
Okay. Other question is that how to measure the energy efficiency, and another question is which component of clay helps in increasing the energy from a fluorophore to another.
Okay. So first one is actually here. In the system, we have two molecules. Of course, intramolecular energy transfer is also possible, but here I am talking about energy transfer between two different molecules. One is donor, one is acceptor. What we do normally, we give energy or at a particular wavelength so that only the donor can accept the energy, that is, can absorb, and it will go to the excited state. Then non-radiative pathway, it come to the ground state, giving the energy to that molecule, provided the condition is suitable for energy transfer. Suitable in the sense distance should be less than 10 nanometer, then orientation factor overlap, so many issues are there. Okay. So then the second molecule, acceptor, will go to excited state, and then it will release photon, and you will see the fluorescence. So this is the whole process. Then how you will quantify it? There are several ways. First way is you can measure the fluorescence of your donor in absence of acceptor. Then you will have some kind of intensity. Then you measure the fluorescence of the donor in presence of acceptor. That is after giving the energy. Then you will see some decrease in energy. By comparing these two, there are standard formula, 1 minus FDA divided by FD. That is, but just by comparing the fluorescence of the donor in absence of acceptor and the fluorescence of donor in presence of acceptor, you can quantify the efficiency. This is one part. On the other way is also there. For example, by measuring lifetime. If you measure the lifetime of your donor in absence of acceptor and in presence of acceptor after giving energy, then you will see lifetime, absence of acceptor lifetime is high because it's coming to the ground state, and in presence of acceptor it is not coming to the ground. It is immediately it is giving the energy to the another molecule. That is, lifetime is decreases. You will see a decrease in the lifetime. So if you measure the lifetime in both cases for the donor, in presence of acceptor, in absence of acceptor, and if you compare these things, then you will have again idea about the energy transfer efficiency. So this is the first answer of the first question. Then the last one, the effect of clay, how clay contribute. I told that energy transfer process depends on several parameters. Main issue is it is a distance dependent phenomenon. Distance, if you and of course distance should be less than 1 to 10 nanometer. Less than 10 nanometer must be. If higher distance, then there is hardly energy transfer. Now, if you lower the distance, then energy transfer efficiency increases. Again, by manipulating the orientation of the molecule, as well as by manipulating the overlap of the spectral overlap. Overlap means the fluorescence spectra of the donor and the absorption spectra of the acceptor, you can manipulate the energy transfer efficiency. So in presence of clay, clay is inert material. No, it's optically inactive with respect to spectroscopy here. In our case, because we are using this UV range. So clay, what clay do? When molecule absorb on the clay surface or they intercalate in between the clay layer, then the distance between molecule decreases. And using there are some standard theory to calculate the distance between molecules. We calculated this and we have seen that in presence of clay, the distance decreases. And again, the spectral overlap also increases. So these two factors mainly contribute the increase in energy transfer efficiency. Clay is not giving energy, but it's helpful to control the conditions or environment so that donor can give more energy to the acceptor. In this way, it takes its rule.
That another question, that why the donor fluorophore radiates non-radiatively? There is no.
Yes, actually, energy fret is a electrodynamic phenomena and mainly depends on dipole-dipole interactions. Okay, so when the fret condition are fulfilled, for example, distance and other criteria, then donor accept energy and it go to the excited state, but the dipole-dipole interaction of the donor occurred with the acceptor, and in this way it gives its energy to the acceptor. That's why it does not radiate. Of course, it releases the photon, but the photon is absorbed by the acceptor. That's why I am telling it's non-radiative. And then acceptor go to the excited state, and finally acceptor radiates. That's why it's a non-radiative process. Otherwise, you will have in the final end, you will have your radiation.
Okay, thank you, Arsad, for your nice presentation. And now this is the end of this second lecture session, second session. And now it is lunch break. After lunch break, we will meet again at 2 p.m. Thank you all. And there is also that assessment link is also available. You just give answer to this assessment link. Thank you all.
Okay. So one announcement is there. Okay, before that, thank you, sir. One announcement is that our next session is a special one, and according to the AICTE and central government mandate, this ATAL FDP must have one yoga session. So our next session is on yoga, and this will be done by a yoga specialist. He is our colleague, of Physical Education Department, and he is expert in yoga. So I request all of you to be on time. This is not only helpful for academic, but helpful for our health also under this pandemic situation. So please be on time and join. Hopefully we all will be benefited. Thank you very much. Thank you.
Dr. Hussain, I am Anirban. I had some questions to ask over the channel. Is it possible that I can ask you the question?
Yes.
Now? Okay, so I had two questions. Very interesting, that alcohol detection strip, the color change. So I wanted to know, did you check the concentration? How low the concentration may go in a person's Excel thing, and then it can still detect it, or
no.
How did you navigate the thing actually? That's what I asked.
No, actually, we have studied it in lab with different concentrations. Okay, but when one people consume, then we didn't check the concentration. That means you consume maybe 10 ml, then inhale, then maybe 100 ml. We didn't check like that, but we checked the concentration in the lab, and it was working good.
Understood.
But
so another question regarding this, I was having in mind: is there any to preserve those thin film coated strips? Means how long does it can be preserved?
Yes, it's long time, because in presence of clay, the clay gives the mechanical stability. Clay main rule is here as a binder. It binds, because clay have this negative charge. It attaches, or cation exchange capacity, or due to intercalation, molecules go in between the layer or attach to the surface. So as a whole, mechanical stability of the system increases. So it's we have checked it. Clay film maybe 6 months, 1 year is stable.
Okay, so
otherwise degrades.
Like relative humidity and any other temperature. I mean to say, does it affect the characteristics of that strip?
No, in that case, we didn't study this one, but we studied humidity effect on organo-clay systems using other material. And in some cases, we have found that humidity affects, but here we didn't check.
Okay, thank you for the nice clarification. Thanks.
Okay, welcome.